All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Alberto Padoan, who is an assistant professor at the University of British Columbia. Alberto is a friend today. I'm very excited to have him give a talk. So I give you a brief overview of his bio. It's very long. He has done many things, but I will try to be brief. So Alberto was born in Ferrara, Italy. By the way, short note, you should all go to Ferrara at some point in your life. It's a fantastic town. He received his laurea magistrale degree or Master of Science in Automation Engineering from the University of Padua, and then a PhD degree in Control Theory from Imperial College London. He was then a research associate in the control group at the University of Cambridge, working among others with Rodolphe Sepulcre. And then he joined in 2021 the Automatic Control Lab at ETH Zurich. That is where I met him, and the NCCR Automation. And he first was a postdoc and then a senior scientist. He then recently joined the University of British Columbia as a faculty, and his research focuses on modeling, analysis, and control of complex dynamical systems. And the emphasis is particularly on geometric and data-driven control, biological applications, and large-scale cyber-physical systems. If you haven't already, you should know Alberto for his podcast that he funded and actually ran since the beginning, which is the podcast named In Control. Besides inviting amazing speakers with different perspectives on the subject, I really admire the depth that Alberto has when dealing with the different speakers, different topics, and also the questions he asks them. So for me, it's one of the best moments in the month is when this podcast comes. I can listen to it, and it's amazing. So I really admire him for this work. And today, Alberto will present a talk titled The Shape of Dynamics. Feel free to ask questions in the chat. We will monitor it and stop Alberto if needed. And again, really excited to listen more to this. And without further ado, Alberto, the stage is yours.
Thank you for the very generous introduction, Joelle. It's a pleasure to be here, and thank you for the invitation. So I'll try to be concise at the beginning. What I want to say is start with acknowledgements and commercials. I promise there will be no commercials after this beginning. So first of all, I want to acknowledge everyone who has collaborated, most of those who have collaborated with me over the past few years. There are many who unfortunately didn't make it to this picture because the type of research is unrelated. And also those who have been teaching with me, this amazing team that I have here on the right of this slide, course Computational Control, which I invite you to Google. It won the best course award at ETH in electrical engineering in 2023. And I think it's going to be something that is going to last. As I promised, also not only acknowledgements, but also commercials. So as Joelle mentioned, I recently moved to the University of British Columbia in Vancouver. Vancouver is a wonderful city, and if you're considering graduate school, feel free to get in touch. There will be positions open on a rolling basis. And finally, as we mentioned also before, I'm also the host of the In Control podcast. This is the first podcast on control theory, entirely dedicated to that. And a new episode has just come out with Miroslav Krstić on essentially partially differential equations, extremum seeking, adaptive nonlinear robust control. It's a super fun episode. I invite you to go and check it out. Okay, now end of commercials, and as I promised, and let's start with the actual talk. So as I also wrote in the abstract of this talk, the motivation for me for the type of research that I'm going to discuss today is really autonomy. And autonomy intended in a broad sense, because what I mean here by autonomy is anything that allows us to, that is interacting with an environment, only relying on data and adapting online. So we see this kind of autonomy in very different shapes in the wild, starting from AI assistants to robots to smart buildings, all the way to large-scale infrastructure that is continuously updating its state through data. And this kind of autonomy has been essentially enabled by a number of technological advancements, starting from hardware advancements, the generation of data, the upgrade of infrastructure that is able to support also the use of that kind of data, But also one technology that is often not mentioned is feedback. Feedback underlies autonomy in every possible way, and it allows us essentially to connect intelligence to a given system and its environment through sensing and perception. And the question that I'm going to investigate in depth today is basically related to modeling systems for the purpose of control and analysis. The question we're going to ask is essentially, what is a good system model? And this type of question has haunted, if you want, systems and control theorists essentially for the whole past century. If you ask this question in the context, say, of electrical circuits, considering, for example, an RC circuit, and you ask the question to, say, George James in the 60s, he would have told you that a good model for a system would have been an input-output relation that is relating inputs to output, and a manifestation of this would be a transfer function. The same question in the 70s during the space race would have gotten a different answer. In particular, Rudolf Kalman would have said state space models are the way to go because they enable more tractable analysis and control. And if you were to ask the same question today, perhaps the best type of model would be a large language model or a neural network, as depicted here with Nobel laureate Geoffrey Hinton. But today I'm going to advocate in favor of a different approach, namely a behavioral approach to systems theory put forward by Jan Willems in 1980s, which essentially characterizes a system in terms of the set of all possible trajectories that it can generate. It's a set-theoretic view to systems modeling, and as I'll try to elaborate also later, this comes with several advantages. It is a compositional theory, it is representation-free, and it is algorithmically tractable. So the take-home message really is the following. We want to be as representation-free as possible. We want to match the representation or the model to a given task, and we should let the shape of the set of trajectories dictate the representation that we choose. I'll try to motivate now why we should consider this approach to systems modeling as opposed to all the other ones that I have shown you before. Well, I think there's at least 3 reasons why this approach is valuable, and these are the following. The first reason is performance. So today we're living in a world where we have an unprecedented amount of data, storage, and computation power. And if you were to give that type of power to a classical control theorist with classical control models, it wouldn't be of any benefit, particularly when we're talking about systems such as large-scale infrastructure systems where we have tons of data and where modularity is really the essence to tame complexity. Complexity is indeed the second reason why we should consider this type of approach, because sometimes models are way too complex to be useful or even conceivable. Think about, for example, perception, soft robots, fluids, algorithmic pipelines, and systems with humans in the loop. I'll give examples also later. And the third reason to me is customization. Customization means here that given the fact that we have all this data, storage, and computation, and also we have the problem of dealing with new levels of complexity, different applications require different tailored operation, if you want, across different users, platforms, and contexts. And I'll try to give examples also later in the context of smart building automation. So now I'm going to elaborate on these 3 aspects individually, giving you 3 examples that I think will be useful also to carry forward my discussion. The first example concerns traffic control. In the past few years, I've been dealing with traffic control applications, and given that I've been living in Zurich for the past 3 years, I thought that maybe this would be a fitting example. So Zurich, in particular, is a city that has 15,000 roads and approximately 800 controllable traffic lights. So we already see the levels of complexity of the systems that we have to deal with. Users operate in a let's say, multi-agent fashion. The system, the dynamics of traffic is highly nonlinear and heterogeneous. Every day is slightly different from the past. And therefore, controlling this type of system is quite hard. what is more performance in this system, so efficiency in this system, essentially means sustainability. Because if you do a very simple back of the envelope calculation, and you take into account that there's approximately 500,000 people moving in and out of the city, traveling approximately 15 kilometers every day, taking data from the road traffic office in Zurich, you can see that it's the level of cars that are going in and out of Zurich every day generates approximately 1,000 tons of CO2 emissions per day. So even tiny improvements in terms of the efficiency of these systems has massive consequences for their sustainability. And I'll give you, so therefore we need high-performing data-driven algorithms, and I'll give you just a small preview about the fact that it's possible just by tweaking an algorithm to save 40 tons of CO2 emissions using data-driven control algorithms. The second type of reasoning that I want to bring forward is the fact that, as I mentioned, Zurich has something like 15,000 roads to be whereby we have to regulate behavior, and approximately 800 controllable traffic lights. And you have to do this in a real-time fashion. You have to do this in a way where failures are the standard, roads are closed, accidents happen. And therefore, the type of algorithms that we have to develop, first of all, need to take into account the massive amounts of data that we have at our disposal, but also be modular, because failures essentially can happen. And also in terms of scalability of the algorithms that we want to deploy, at the moment, it would not be possible to control in a centralized fashion systems of this size. So I argue that we need modular data-driven control algorithms, and I'll try to show you later how to do that. And finally, the third application that I have in mind here is related to each of these individual homes on Lake Zurich that are essentially themselves autonomous systems. These systems, in fact, are fitted with an enormous amount of Internet of Things devices, as they call them. Every house today is full of sensors, and it's estimated, according to Statista.com, that the number of IoT devices is expected to double in the next 5 years. We're talking about billions of, approximately 30 billions of IoT devices, and these will generate a lot of data, but most importantly, will allow us to control these kind of systems better. Now, what I'm trying to display, what I'm displaying below here is a smart energy valve that of an important company from Switzerland that essentially allows you to control in a smart fashion temperature in a building. And the requirements that these new companies are asking to these devices is to operate, first of all, in a way that is reliable, and reliable means not necessarily connected to the internet. These devices are dealing with systems that are thousands of inputs and outputs and not much physics, because even though we know how heat propagates, humans operate inside of these systems and therefore change the operating conditions and therefore give rise to wildly different parameters. And also we have to deal with small data, in fact, with latency, because these systems operate with hardware that can only run very simple routines. I was told by one of the engineers working in this company that the largest matrix that we can invert is 100 by 100. So good luck with that with any machine learning algorithm out there. And what we would like to do in this context here, for example, is to have models, as we were mentioning also before at the beginning, that are capable of adapting and spotting anomalies like the one that I'm showing here. So in this case, we need adaptive data-driven algorithms, and we need models to adapt to these requirements. So we're faced with what I call a challenging trilemma, meaning that we want data-driven algorithms to be performant, we want them to be modular, and we want them to be adaptive. But normally, you only have one of the three. And the idea here would be to actually get to the summit of this famous Swiss mountain, whereby it is possible to have algorithms that are both, that are performant, modular, and adaptive. And I'll try to convince you that it is possible using this approach, the behavioral representation-free approach. So here's the menu for today. We're going to first start with a refresher with behavioral systems theory in a nutshell. Then we're going to move towards 3 types of applications whereby we'll talk about representation-free modeling. I'll show you different shapes of dynamics. I'll show you that depending on the shape of this the dynamics of a system, we can tailor scalable data-driven control algorithms, and we can also use new ways of adapting, essentially using gradient-based algorithms, but on different sets. So let's start from behavioral systems theory. So for those who haven't seen it before, I'll give a refresher for this talk to be self-contained. But basically, behavioral systems theory was put forward by Jan Willems in 1986 with a trilogy of papers titled From Time Series to Linear System, whereby he asked the same question that we asked at the beginning of this talk: what is a good model for a dynamical system? Well, the conclusion, or if you want, the proposition of Jan Willems is the following: dynamical systems should be regarded essentially as sets of trajectories, that is, functions of time, and summarized nicely also by this quote that he has: the behavior is all there is. The behavior is all there is, meaning that everything we see, everything we measure is just trajectories from a system. Models are abstractions. So what you need in order to define a system is a time axis, which allows us to talk about time evolution. You need a signal space that then allows you to define trajectories over time, here called W of t. And finally, the third ingredient is the behavior of the system. So that is essentially a set that incorporates all possible trajectories of a given system. So every point, if you want, of this set is a time trajectory. And you should notice that here we're not being prescriptive in terms of what kind of representation we may want to use. But the nice feature of behavioral system theory is that it accommodates all other possible representations of a system. So in this sense, we can regard the system as a transfer function, as a state space model, or even as a neural network, depending on the application at hand. The second nice feature of behavioral systems theory is the fact that we do not distinguish inputs and outputs, meaning that normally what we do is we define a vector, if you want, of W's, whereby we have inputs and outputs of the system. Sometimes we happen to know what is driving a system. Say, for example, in this RC circuit, we are driving the system through a voltage that we control. But sometimes, specifically, for example, in circuits, it is difficult to tell what causes what. And finally, the properties of a system essentially are reflected in the shape of the behavior of the system. For example, linearity of a system is reflected by the fact that B, the behavior, is a subspace, so it respects this law. Similarly, time invariance of a system essentially manifests by the fact that if we shift a trajectory in time, the trajectory is still in the behavior. Okay, but what do we mean now by the shape of dynamics? And what does this bias actually in terms of modeling? Well, perhaps the most recent interest in behavioral systems theory has been manifested again by the fact that we can bypass this traditional way of modeling systems, whereby we have our own system, we measure, let's say, some data by probing the system, and then we build a representation thanks to system identification algorithms. Well, another approach is that of behavioral systems theory, whereby instead what we do when we model a system is rather build the behavior of the system. And in particular, if we're interested in finite horizons, what we can do, if we happen to know that the system is linear and time invariant, well, we organize time samples of our measured trajectory. In this case, for simplicity, I'm only considering one, but in principle, you can have many and also measured under different operating conditions. You organize this data, as I mentioned, in a data matrix. And if a certain rank condition holds, in this case, the rank condition means just that the rank coincides with the number of inputs times the horizon over which I'm interested, plus the order of the system. Then I know that the column span of this matrix essentially generates all possible input-output trajectories, all possible trajectories of the behavior. So a trajectory is in the behavior over a finite horizon the finite horizon 1 to t, if and only if it lies in the image of this matrix. And you can say, okay, but well, there's many different other properties that we can impose on or assume, if you wish, on the structure of the behavior. For example, here I'm listing just a few, as we investigated in a recent paper at CDC with Florian Dorfler and John Ligeros. There's many other different types of sets out there that have enjoyed different properties that lead to tractable algorithms, for example, conicity, convexity, and even affine sets. And you may ask, okay, where do these properties actually manifest in the real world? Well, there's plenty of examples. Here I'm listing just a few for you to think that, okay, this is not just abstraction, but it's actually something that we encounter in real life. For example, diodes or pipes that unidirectional pipes, if you wish, generate conic behaviors. Constraints, unilateral constraints imposed on linear systems generate convex systems, and affine systems arise in the context of systems with offsets or from linearizations of nonlinear systems. And you may ask, okay, what does this buy me? What does imposing these properties buy me? Well, first of all, we can obtain different representations analogous to the representation that I mentioned before, but most importantly, we can save on data. And as I mentioned, saving on data in some applications is important. I do have examples concerning, a simple example concerning how to use these properties as backup slides, but I think it's most fun to actually move on to the fun part, that is control. So now we move on to the actual control part, where we use these kind of representations in order to, say, solve problems like the one that I posed at the beginning on traffic control, and even leading to scalable algorithms. So this perspective, representation-free perspective, has led to, most recently, to some important developments in the context of data-driven model predictive control, but it all starts in 2005. Actually, I believe this is a typo, in 2008, with a paper by Ivan Markovsky and Paolo Rapisarda, whereby they realized that this perspective essentially allows you to solve a classical problem, namely linear quadratic tracking, as essentially a least squares constrained problem. How does this work? Well, first of all, we realize that linear quadratic tracking essentially consists in the following problem. We're given an initial trajectory of, say, inputs and outputs that is fixed and that we measure. And now we're trying to optimize a future trajectory that is as close as possible, if you wish, to a given reference. The reference is not necessarily feasible, and therefore it does not necessarily belong to the subspace spanning the finite horizon behavior of the system, but we can try to minimize this distance in order to obtain the optimal controller, if you wish. Posed in a representation-free way, this essentially can be posed as follows, whereby this wedge just means that we're concatenating in time two trajectories. And as you see, the optimization variable is W future. Now, why is this important? Well, this is important because most recently it has enabled a lot of data-driven predictive control algorithms, which essentially solve the same problem in a receding horizon fashion. And if you do that, basically by choosing different representations, if you look at it from this perspective, by choosing different representations, you see different algorithms at play. For example, the by now famous data-enabled predictive control developed by my friend Jeremy Colson, also at ETH with John Ligeros and Florian Dorfler, essentially goes on and exploits this, if you want, parameterization or representation of the system behavior in terms of the span of a Hankel matrix, adding on top of this some regularization to the G variable, which also is an optimization variable, which is not appearing here. If you take a different model for the behavior over a finite horizon, say, for example, an affine system, you obtain a different type of algorithm developed by colleagues at the University of Stuttgart, Julian Berberic and co-authors, that basically add a different type of constraint here in order to capture the fact that for nonlinear systems, slowly varying nonlinear systems, the linearization is actually a affine space. But perhaps the most fun part is actually that of applying these kind of algorithms. And what we did in collaboration with Alessio Rimoldi and Carlo Cenedese, also at ETH Zurich, was to just for fun apply these kind of algorithms to the problem of traffic that I mentioned at the beginning. What we did was to team up with Transcality, which is a Zurich-based startup that is developing essentially very faithful and then highest possible fidelity digital twins of cities, in particular in this case of the city of Zurich, using the software Sumo that allows you to essentially model the individual behavior of different agents in the network. As you can see here in this simulation, you have low congestion in green, high congestion in red. And I recall that you have approximately 800 traffic lights and 15,000 roads. Now, what we did, as I mentioned, was to measure data from this digital twin using, for those who are familiar with the term, macroscopic fundamental diagrams to agglomerate, if you want, model homogeneously parts of the network. And then we applied a vanilla data-driven predictive control algorithms to see whether we can improve on the state of the art. And the results were astonishing in the sense that without much thought, what we obtained was an improvement of 3% on travel time with respect to state-of-the-art algorithms, which translated into an approximately 3% improvement in terms of CO2 emissions, which doesn't seem like a lot, but if you multiply by the number of cars flowing in the network every day, we would be saving, if we were to deploy these kind of algorithms today, we would be saving something like 40 tons of CO2 per day, which is mind-blowing to me, given that we're just tweaking an algorithm. Now, you may argue it is difficult to deploy these kinds of algorithms in the wild, but you will probably be surprised to learn that the most advanced traffic control algorithms in place today, say, for example, in Philadelphia and Sydney, are essentially building on rudimentary forms of model predictive control. So there is hope of actually applying these kind of algorithms in the wild. And what I want to show here is just a simulation giving you the impression of the type of improvements that you can get. On the right-hand side is a congested scenario whereby we don't apply these kind of controllers. And on the left-hand side, instead, we have a scenario whereby we apply these data-driven predictive control schemes that essentially lead to performance of a very high performance in terms of low congestion. Now, I mentioned at the beginning that this kind of network, however, has approximately 800 controllable traffic lights and 15,000 roads that we want to regulate, in which we want to regulate the traffic. So the question arises immediately as to how do we actually exploit knowledge about the structure of these networks, and in particular, structure in the form of topological information about how the roads are connected to one another. So if we were to deploy, again, these vanilla algorithms in real time, this would be problematic because the number of inputs and outputs that is symbolized here by Q, and also the number of time steps in the future influence how quickly can we solve these kind of optimization problems. And this is problematic in real time. So we really must use information about structure in order to scale them up and turn them into distributed algorithms. Now, and this is just the motivation, as I mentioned, the traffic in the city of Zurich. So now I'm going to talk about a way how to distribute, if you want, these kind of algorithms in a representation-free way, taking information from the graph structure of the network. So suppose that we now start with a system whereby each subsystem, for example, road in the network, is represented by these purple blocks. And these systems are potentially also interacting with the environment through, say, these arrows. And these systems encode, or the whole system, if you want, encodes information about topology through these pink solid lines that connect each individual subsystem. Now, suppose that we want to solve now this problem leveraging this kind of information. How do we do it? Well, we can realize that, in fact, the behavior of the system is essentially determined by the intersection of two sets that have a very particular structure. So on the right-hand side, we have all interconnections, so the topological information that I was talking about from the network. And on the left-hand side, we have the set of all possible individual isolated subsystems, whereby we assume that there are no interconnections. Now, suppose that, moreover, each of these systems is linear, but in fact, convexity is enough and closedness is enough. And suppose that we interconnect these systems via full interconnections, meaning that the variables of one system are equal, of, let's say, the ith subsystem is equal to the jth variable of the jth subsystem. We can also talk about partial interconnection. That is not problematic, but for simplicity, that's what we're going to assume. Well, in this case, it's not easy to see that, it's not difficult to see that these systems are actually subspaces, here by assumption and here by the structure, if you want, of the interconnection. But not only that, we can see that if we want to characterize, if we want to compute feasible points or points that lie in the intersection of these systems, well, we can use so-called alternating projection algorithms. And this really gives rise to the name split as a pro, because we're splitting, we're performing, if you want, control by splitting using operator split, splitting the optimization problem using operator splitting methods, and then applying scalable alternating projection in order to compute efficiently projections. So this is important because it allows us to scale the algorithms that I was telling you about before, but also these kind of algorithms do not require linearity. So if we want to deal with large-scale complex systems and whereby we replace complex with nonlinear, we can do it, assuming that the underlying behavior is convex. So the shape really determines whether it's possible to apply this kind of algorithms or not. Secondly, the representation-free perspective allows us to integrate different models together. In particular, each of these BIs can be represented, for example, using one of those representations that we've seen before. So the image of a data matrix, in case we don't know the system well, but we want to model it through in a data-driven fashion, let's say, but also potentially in different ways. And we can instead model parts of the system in a model-based fashion if we think that we have good estimates of the parameters of a model that represent well the system. And finally, we can also handle constraints, because in fact, we don't really need to have just the intersection of two sets, but we can add more sets to the picture. And what we would obtain is no longer what we call von Neumann's iteration, whereby we iterate between these two subspaces to compute a point in the intersection, but instead Dijkstra's algorithm to compute, again, the projection onto the intersection of these two sets. And these projections, as I mentioned, well, as I wanted to mention, are cheap. The reason is that when projecting onto a Cartesian product, the projection distributes. And also when projecting onto a graph network, what you obtain is essentially a consensus step. So these type of algorithms are really efficient, as also illustrated here. So we tested this kind of idea on different topologies, for example, on the line topology, on the ring topology, and on the mesh topology, and we consistently outperformed the state of the art in terms of computation time, with the additional advantage that we no longer rely on a single representation, but we can pick and choose essentially what fits best different subsystems. Not only that, but we have also tested the same type of algorithm again with respect to distributed algorithms as we increase the number of edges, or if you want, if we increase the connectivity of a graph. And again, we can see that at some point, the running time of distributed control wins over the centralized version. And finally, I want to talk about adaptation. So adaptation in the sense of how do we choose, if you want, what type of shape should be depending on the task at hand. Well, one motivation for this type of question is the following. if you try to apply these kind of data-driven predictive control algorithms in the wild, most of the times they will actually fail unless you tweak tuning parameters intelligently, because most systems out there are nonlinear and time-varying. And therefore, these type of algorithms, which assume that the system is instead shift invariant and therefore time invariant, do not perform well, unsurprisingly. So the answer to this problem is, in fact, that of starting to assume that a system is no longer time invariant, but acknowledge the time variance of the behavior of the system, which, for example, for a linear system that is not time invariant, will consist in having a model that is essentially a subspace that changes over time. And so we use this kind of idea in the context of online identification for identifying, for example, faults. And given that the set of all possible subspaces in a given vector space is a manifold, and in particular it's called the Grassmannian, we thought that if what we could do is track the representation over time by updating it using a gradient scheme. And what we obtain is basically very good performance that matches the state of the art, as you can see here below. This is to recall the application also that we have in mind. In blue and red, they're quite overlapped, so it's not easy to see, but we're matching state-of-the-art in terms of online system identification algorithms, with the added benefit, however, that given that we deal with a gradient scheme, first of all, we adapt better in terms of transients. So here in red, you would see a standard recursive least squares algorithm, and in blue instead our algorithm. So the overshoot in terms of prediction error for our systems, for our adaptive, if you want, online system identification algorithm is smaller, but it also comes with guarantees, because every gradient system has some kind of input to state stability property that we can leverage to provide guarantees about how quickly we converge to the true subspace, assuming that indeed the system is linear but time varying. And I should also mention that we did apply this kind of algorithms also to the application that I mentioned before. So, for example, the idea of spotting faults in these kind of systems, and we obtained very good performance that was matching essentially that of most common machine learning algorithms, with the added benefit that, however, the routines that we were implemented required essentially much easier linear algebra computations. And here is just a depiction of how the algorithm works in practice. For example, here I'm showing you how a subspace tracking algorithm works on a Grassmannian that is essentially defined on by the set of all possible vector spaces of dimension 1 in 3D. So we can identify those subspaces with points on a sphere. As you can see in black, we have the iterations of our algorithm, and in red, instead, the subspace that changes over time. And as it changes, the algorithm, essentially being gradient-based, follows the distance. It tries to minimize the distance to the red points, achieving essentially the performance that we designed it for. Okay, so I hope that I did convince you actually that it is possible to obtain performant, modular, and also customized or adaptive algorithms adopting this representation-free perspective. But you may ask, what is next? Well, I just decided to have one slide whereby I wanted to give food for thought and essentially draw your attention to upcoming publications that we will have on the subject, whereby I think we are trying to address some of the most important questions related now to modeling. In particular, in everything I said so far, I didn't give you any characterization of uncertainty. So everything I did until now was deterministic and did not acknowledge a stochastic perspective. The reason for this is that stochastic behavioral system theory is actually still an active area of research. Defining what is a stochastic behavior is in fact hard. And so this is something that we're working on with colleagues at ETH Zurich, and there is an upcoming publication also at CDC at the next CDC that I hope you will be able to appreciate soon. As I mentioned before, the behavioral systems theory approach is essentially representation free. So all models that we have considered so far are in a way classical models, meaning that we have dealt with subspaces, state space systems, transfer functions, but understanding how does this theory actually interrelate with new models that are originating from different areas, for example, machine learning, is, in my opinion, something that is very relevant and valuable. And finally, as we talk about those kind of systems, so systems that originate, for example, in machine learning, for which we have no guarantees at the moment, or at least in part. I know that this is debatable, but one thing that we are good at doing, at least as control theorists, is that of providing guarantees using, for example, our familiar Lyapunov arguments. I think that, or safety arguments, as we call them today. What I wanted to say is that connecting now these last two items together, I think would be extremely valuable in the context of behavioral systems theory, but also for applications in the wild. I think I'm relatively early on time, but with this, I thank you for your attention. I want to reiterate the take-home message of the talk of today, and that is essentially stay as representation-free as possible, delay the choice of the representation to the last possible second, match the model to the task, meaning that let the task decide what is the most appropriate representation that you choose. And finally, shape, as I mentioned, should guide the selection of the model itself. I know that I promised not to have any other shameless plug today, but instead I'll mention it again. If you're interested in having a doctorate in Vancouver, please check my website. On a rolling basis, there will be openings. And also, if you haven't heard it before, please go and check out the In Control podcast. Every like counts for funding. Thank you so much for your attention.
Thank you, Alberto, for the great talk. And no worries about the shameless plugging. It's great. So let's open the stage for questions. Guys, you can either raise your hand and ask directly, or I can read from the chat. There is already one on the chat from Hamad, who asks, in the decomposition of the graph to subsystems and connectivities, so this slide where you had the two behaviors, could you clarify how we can find an intersection between sets where their elements are in different domains? I think that's the question.
I'm not entirely sure whether I understand in different domains, but the idea here is that a behavior is defined by a set of equations, let's say. And this set of, in particular, if the behavior is an interconnected behavior, there will always be a set of equations that describe, if you want, the interconnections. And these we can leave aside, let's say, to the left-hand side, sorry, to the right-hand side. And then there will be another set of equations that describes, if you want, how the dynamics of each individual subsystem evolves. Now, the partitioning these sets of equations in two parts allows us to, first of all, exploit the fact that what we call the network behavior, or the behavior defined by the interconnection constraints, is almost always linear, and it's almost always easy to project on, meaning that the projection is essentially a consensus step. And this is also something that arises very frequently also in optimization when you want to distribute computation, say, for example, in algorithms like ADMM. On the other hand, if you want to project on the set of all possible isolated subsystems, the projection is also easy to compute if it's easy to project onto the individual subsystems. The reason is that if you want to project onto a Cartesian product, the projection onto a Cartesian product is the projection onto each individual element in the product, if you want. So this essentially allows us to scale and compute projections way more efficiently. We can parallelize, if you want, the computation of projections, and therefore, if we're able to make sure that the bottleneck in an algorithm is a projection, then we can use this approach. I hope this addresses the question.
Yes, it seems so, Ahmad. In case not, please follow up. Oh, yes, it does. I go ahead with another question I had, which is, so this is super interesting, and I think the compositional structure you are showing here is very interesting. I was wondering, is there a compositional structure that emerges between systems? Here is kind of within a system, you can exploit these properties, but can you solve interconnected systems or control problems of interconnected systems where systems behave like this or are controlled like this in a better way? So I'm kind of zooming out an extra layer and trying to interconnect various data-driven predictive control problems with this structure.
I think this is an extremely relevant question, and in fact, I cannot resist and go and pull out one of the extra slides that I
did. Please do.
Essentially for you, because I think that's actually a very good question. It puts the finger in the right spot, and it's basically the fact that autonomy these days is composed of all of these. Let's say autonomy stack. This is taken, by the way, from a paper by colleagues at ETH. Autonomy is very often described in terms of these kind of block diagrams, as you know, also, Joelle. And each of these diagrams is itself an algorithm. Yes, so the answer is it is possible to use a behavioral perspective on this kind of problems. And in particular, the only thing that you have to change is really what you choose as the signal space, the time index, and the behavior. But per se, it is possible to use that kind of modeling. And in fact, I think it's very close also to a compositional, let's say, categorical way of characterizing diagrams by leveraging behaviors, if you want. And I think this is very practical because there's always different types of complications, for example, real-time requirements, privacy concerns, attacks, and whatnot. And what we care about is really giving guarantees in this kind of context.
That's fascinating, very interesting. I think it opens up a nice studies. I have another question, but maybe let's first ask anyone in the audience. Oh yeah, Mohammed, please go ahead.
Thank you so much for the presentation. I had two questions. My first question is that usually in this framework, we assume that a couple of past input and past output is a kind of abstract state of the system. And my question is that why we do not use the latest output measurement to build this abstract state? And my second question is that between Koopman operators and this LPV estimation of the nonlinear system, which one do you think is the most promising solution?
I think both are interesting questions. So the first question relates to, I'll try to translate it and then you'll tell me whether I'm doing a good job. But the WINI here essentially defines the initial condition of the system if we take it long enough. This is certainly true for linear systems, but in general, it's not true for all types of behaviors. Now, that's, I hope, an answer or a partial answer to the first question. The second question is related to representation. So you mentioned Koopman operators and linear parameter variant systems. I think all those, let's say, representations or properties of a certain behavior shape, if you want, the dynamics of the system. And that's exactly what I'm trying to say. So depending on the shape or depending on the prior knowledge that you may happen to have, you may choose a different representation. But the beauty of this framework is that you can postpone, if you want, the choice of the representation to the very last stage. So this formulation, for example, is saying minimize the distance between these two trajectories, whatever system you might happen to have. This could be nonlinear, this could be linear parameter varying, And in one application or the other, let's say Koopman might work better than linear parameter varying or vice versa. And this typically is informed by, as I said, the shape or a priori information. I hope this addresses, at least in part, your question.
Yes, thank you. Thank you so much.
Great. Any other question for Alberto? Yeah, I'll go ahead and shoot mine. I just more of a curiosity. So is there literature that explores this behavior approach, adding some preference over the elements of the set? So essentially, right now you have sets, you have intersections, but there are very nice algebraic structures also for partial orders, for instance, or sets with extra properties. I'm pretty sure it will complicate the optimization problem you are solving or this control problem, but I'm curious if there are previous efforts in that direction.
Again, wonderful question. I think definitely spot on and something that I thought about myself. So I interpret it as, if you want, adding, so we mentioned at the beginning that there was, to define what is a behavior, you have to specify a time axis, a signal space where signals take place, if you want, and then the behavior. I think in general, one could also add to the definition, say, another define a dynamical system as a quadruple, whereby the fourth element is a set of attributes that we attach to a given system. And then that would actually give the structure that you're asking to, let's say, modeling. And I think it's actually a very interesting direction, particularly for what you mentioned before. So the zooming in or zooming out part, and generally speaking, how to incorporate even more information about a system. I hope this makes sense.
Yes, definitely. That's okay. That's very cool. And maybe my last question I had, I wasn't up to speed with the results on the traffic control. So the collaboration with Transcality is extremely cool. One thing I wonder is, sometimes when you explore these compositional properties, there is one very nice one, which is you have guarantees when you do refinement. So for instance, when I say refinement here, I mean, for instance, in this context could be coarser or finer representation of the network. Maybe instead of looking at each node, you aggregate nodes together and you aggregate behaviors. Is there some kind of hope there for making it scale to even larger networks? I know you mentioned there are many vehicles, many road, many edges, and so on.
Again, a wonderful question. Every question is spot on. So we did notice, as maybe I didn't mention it in the talk, but what we noticed is essentially that these type of algorithms work when you agglomerate regions of the network into homogeneous regions. Only at a certain scale we can see that there is a linear relationship between inputs and outputs, and in particular here the inputs are the duty cycle of traffic lights at intersections, and the outputs is the density. And at some scale, actually, this relationship breaks. So understanding when is it possible to model, let's say, through, say, subspaces, a network, and when you cannot, is actually an open question. And I think it's a very cool one because it has to do with scale. So control across scales is very much open, at least from my perspective in this context.
Very, very interesting. I will have a look at the paper. For some reason, I missed this paper. I know. I knew you and Carlo were working on these topics, but
way too many.
Too many things to keep track of. Thanks so much. Any other question maybe last question for Alberto? All right, it doesn't look like that, but so he left comments. He left the link for the website also for In Control. Please, everyone listening, go and check. This is great material. And Alberto, thanks so much. It looks like you're opening a full set of problems to explore. That's amazing, and I'm really looking forward to seeing what happens there.
Thank you, and have a good day.
You too. Thanks everyone for joining.